Good evening, everybody.
Hello.
Announcements, trying to think. Friends of Medicine, we have 2 left, Wednesday, and next Wednesday are the last 2 for the semester. Anything else you can think of that I needed to mention for announcements? Alright. So, I really hope that a majority of you guys did the activity 46. It is a highly conceptual chunk of what we need to be thinking about to do a lot of our calculation problems. If you have not done it, turn it in. My policy is 10% per day late, so you can turn in after now for 10% off until tomorrow this time, kind of like, that's how I do it. So if you haven't done it and you have time, complete it, you can come turn it in to me. Let me know when you turn it in, because if you drop it off in my office and I don't see it for a day or 2, I won't know it's there, so please email me with when you drop it off. We're going to be working on a whole bunch of questions that are based on the idea of, is the proton acidic or not? And that's what that whole activity is about. Will it be good? So hopefully you got that out of the activity. If you did it on your own and that wasn't quite the take-home, then hopefully some of the discussions we're having will help that fit. Otherwise, we can try to meet up with me at some point, or talk to the people that went to some of the supplemental instruction. Alright, so let's get right into it then. Go ahead and read question number 1 on the worksheet, answer this question, and I want you thinking about why you would answer this. So basically the question is, we have a solution with a ton of HCl in it, and then we add 1 mole of hydroxide. Which of these answers makes sense?
Thank you. I was like, oh no. Oh, wait, Sarah, I did you lose the money?
Alright, we got everyone clicked in?
It's okay.
So what am I getting at with this question? Does anyone have a feeling for this? What's that? What rules? Okay, so dissociation and acid-base neutralization rules. When you put HCl in water, what forms? H3O plus and Cl minus aqueous. When you put sodium hydroxide in, you get 100% of it, in theory, dissociates into sodium plus, hydroxide minus. So the question is, you have a strong base in the presence of a strong acid. Is it going to completely react or partially react? And the rules, Aurora, are... So we're going 1 step beyond that, though. So they fully disassociate, but then the question is, do they fully react? And the answer is yes. So the definition of a strong base is, when in water, if there's any acidic protons around, weak or strong, it'll react until one of them is consumed. What do we call that kind of a reaction in first semester? Limiting reaction problem, right? So we're seeing which one runs out first. If you don't know that it completely uses up the other one, then you don't really know how to, is it an equilibrium problem? Is it a limiting reagent? We really don't know how to do that. So I really want us being on the same page about this. Strong acid and a strong base are always going to react until one of them is completely gone. We have to know how many protons are there. And so that's something else we'll talk about a little bit over the next couple of days. So then our second question, how do you guys feel about this? Go ahead and talk to your neighbor, See how you answer this question. And I have a diagram of formic acid drawn in the top right corner. Structure.
So, are you saying like any base or like just strong base? Any base?
Is this question different than the last one?
Yes. The first one was added to a strong acid. This was added to a weak acid. Alright, go ahead and click in your thoughts. Click in your answer for now. So what's the difference between this and the last question? So last one was about a strong base and a strong acid. Now we're doing a strong base and a weak acid. What's different about a weak acid versus a strong acid?
Less of it dissociates.
Great, less of it disassociates. We have less H plus ions for every mole of acid that's in there. Love? We're not going to get quite there yet because that's only if you have a mixture. So we'll hold off on that thought a little bit. Why does it disassociate less? Say again?
Is it because it's more stable when it's
Right,
together?
so carboxylic acid is a little bit more stable. You'll find more of the OH together than apart, but it does separate some of the time. And so with this question, I want to drive home the point that regardless of what kind of acid, if it's an acidic proton, we have a definition for that based on that activity 46 that you guys went through, and we can tell how strong of an acid it is based on a couple of factors about what's around it. So looking at a Ka, we say that if there is any acidic proton in a molecule, that we're going to have a limiting reagent problem. Which one runs out first? Do we use up all of our weak acid and then still have excess OH minus after? Or do we have more of our weak acid and then we end up using up all our OH minus and having some weak acid left after? So the next series of problems, going back to what you guys did in the lab with titrations, hopefully this is going to help clarify some of what you did, because those were all limiting reagent problems between strong or strong and weak. It's always going to be a limiting reagent problem. The only time you don't have that, if it's a weak and a weak together, which I don't think you guys did in the lab. Is that true? A weak acid with a weak base, or a weak base and acid together. Say again? Yep. So you did NaOH, strong base, and a weak acid. So one of them is always strong. You will not do a titration with two weak. It doesn't make sense. Then it's not a limiting reagent problem. You don't have the reaction going to completion. So what we're saying is that whenever you see hydroxide from sodium, potassium, calcium, right, any of our strong bases that you guys have memorized, or if you see one of our strong acids, one of those 6 that you have memorized, you're always going to draw an arrow that looks the same. What kind of arrow is that? Is this the right arrow for a reaction involving a strong acid or base? So there's 2 steps with a strong acid. One is you're going to dissociate the strong acid into an H plus ion and whatever that anion is. So in the case of the first equation, you would have HCl goes to H plus Cl minus. Then you say, I have a strong acid, it generated H plus, so I'm going to see what base is there to react with. If we have OH minus in that solution, like we did for the first question today, we're going to say, well, which one runs out first? Which one do we have more of? 1-to-1 stoichiometric ratio. This problem, on the other hand, is you have a strong base and you have a weak acid, but because one of them is strong, we still draw this full-headed arrow. This is a neutralization reaction. One of them will get consumed completely until there's nothing left. We have to figure out how much we have to start with, what the change is, and how much we're left with. Do we use an ice table to figure that out? What do you guys think? Talk to your neighbor. Do we use an ice table to figure out how much is left in a limiting reagent problem? All right, so let's do a thumbs up. Yes, we use an ice table. A thumbs down. No, we don't use an ice table. Thumb to the side. I have no idea. I see almost a 30-30-30 mix. What do we need in order to do an ice table?
Initial.
Okay, well, we need initial change equilibrium, but like,
A lot of things.
what type of a problem do we solve with an ice table?
Equilibrium.
Equilibrium. So if we don't have an equilibrium constant, we can't use an ice table. What's our equilibrium constant when we have a full-headed arrow?
0.
It's infinity, right? It's a really, really big number on the product side, little on the reactive side. Okay, so we don't use an ice table at all. It's a limiting reagent problem. You guys may have some ways that you did it first semester. I'm going to show you what I think is an easier way. It resembles an ice table, but it is not an ice table. Let's be really careful not to use ice tables when we're doing a limiting reagent problem. We'll work through it a bit today. I'm going to call it an ICF table. It's literally like... You guys are going to love it, trust me. It'll be good. So, take home from the first 10 minutes of class, strong acid or strong base, if it is in the presence of the other, it's always going to react completely. We good with that? Let's take a look at a couple other examples. So those top two, that's pyridine, is the compound with the nitrogen. Hopefully you know that other compound. Maybe not my finest question ever, but I want you thinking about what can a H plus from a strong acid do. Go ahead and submit your answer. We'll talk through it. All right, closing out. So Josh, can I give you a volunteer what you were saying a second ago?
I think, I'm going to PG it, I think H goes to everywhere.
What do you mean by that?
So far we've seen it hop, skip, and jump around bases, acids. It doesn't matter. It's just like we're going to hang out, just flip sides.
Okay, there's a lot in that statement, and maybe I'll formulate that to a more concise statement.
C is what I think.
You think one proton will
sorry, I
protonate
said it
two
wrong.
basic
Sorry,
sites?
No. I didn't read what I just said. It goes everywhere. I put
Okay.
it in the answer because I didn't want to miss on putting something in.
So the reason I said this question wasn't worded amazingly. So I like what you're saying about if it's from a strong acid, that proton is going to get used up. It's going to go to any basic site and it's going to protonate it. So it depends on what the ratio is of how many of each we have. That's why I realize this is not the best question I've ever written. But if we have one proton, we'll protonate one basic site. It's kind of what I was trying to get at. So this is, yeah, that's why 1 mole, yeah, it's not a good question. Great. So if it was in the presence of this guy, it would form a quaternary ammonium, meaning quat being 4. So that lone pair would, instead of being a lone pair, it would become a bond, and you would have an ammonium. Pyridinium is the name of that compound. Remember, if you hear a ium in the end of the name, yeah, it's a bad ium. Like ammonium, then that's going to say it's a positively charged nitrogen with 4 bonds. Or, if it was in the presence of bicarbonate up there, then you would end up with the proton being accepted there. Trying to drive home the point, strong acid, doesn't matter if it's a weak base or a strong base, you're going to use it up until one of them's gone. So, an example of the balanced chemical reaction, a 1-to-1 stoichiometric ratio between an acidic proton, right? This is not the net ionic equation, because I still have nitrate in there. But it's going to combine with a lone pair of electrons on nitrogen. If it only has 3 bonds in a lone pair, it's going to act as a base. It's going to accept that proton. I think I have the other one written here as well. It is the most interesting class of the semester, I agree. All right, so same statement. Regardless of if it's a weak or a strong base, a strong acid is going to be part of a limiting reagent problem. So what do we have to think about? How do we think about the acid? What terms are we thinking about here? How do we figure out which one's limiting? What do we have to do that we haven't done for a while to think about limiting reagents? Stoichiometry, balanced equations. Can we use molarity? Can you say I have a 1 molar and a 1 molar solution? They're going to cancel each other out.
No.
What if I have a lot of one of the 1 molar solutions and a little bit of the other 1 molar solution? So what kind of units are we going to be talking about when we're going to try to find the limiting reagent?
Molar mass.
We're going to have to find the quantity of each of those reactants. Without the quantity and the stoichiometric ratio, we're not going to be able to figure out which one is what. We're going to go back to a lot of that first semester stuff that you guys are so good at. All right, so my learning objective for you guys today is I want you to be able to suggest how we make a buffer. There's a couple different ways. We've already hinted at it some last class. And then we're going to do some more calculations of the pH of a buffer solution, which you guys have already done some work with. But here's what's going to change. We're going to say, we have a buffer, what's the pH? And then we're going to add a strong acid or a strong base to that buffer and see how the pH changes and calculate that change in pH. You guys ready for that? Just like titrations. Super easy, right? And then we're going to start talking about titrations. So I want to look at a titration curve for a weak acid, titrate with a strong base, a weak base, titrate with a strong acid. I want you guys to be able to differentiate those. And then the difference between what that looks like versus a strong titration as well. We should be able to tell just by looking at a graph what kind of titration it is and to figure out what the identity of the analyte is in all of those. And along the ways, I want you really to be able to describe how a buffer works, what it is that it actually does that results in the outcome of what you guys know. So, let's start with this set of questions. Question number 3, what makes up a buffer? What's in a buffer? Question number 3? Question number 2, which one was that? So with the wording that I wanted, which wasn't on there, is that 1 proton would consume 1 basic site. So go ahead and write down your definition of what is in a buffer. I also want you to write what does it do, and then we're going to talk about how you make it. make sure to write down your best guess at a definition, or what's in it, what it is, what it does.
Make sure it's acid conjugate base. But you can totally de-escalate.
Great, I love that terminology. Oh, so that's what it does. And what's in it? Alright, so maybe before we dig into this, let's go ahead and get it out there. What does a buffer do? What are they known for doing? Can I get a hand raised? Your voices, Austin?
Resisting change in pH.
Great. It resists change. And can we have maybe even more specific wording than resists? Minimize. Okay, because resist might mean that it doesn't actually change. So we need to admit that no matter how good our buffer is, you add an acid to it, pH is going to change. Which way is the pH going to go if you add an acid to any solution? It's going to go down. Alright, so let's get it out of our heads that it stops changes in pH or some form of that. So it does still change. So how does it do that? How does a buffer minimize the changes in pH? Let's first talk about what's in it, and then we're going to come back to that question. So what is a buffer made of? What's in a buffer? A weak acid and its conjugate base. I heard a number of people say a weak acid and a weak base. That's too broad of a statement. I don't want to hear that. It has to be a conjugate acid-base pair. If they're not a conjugate acid-base pair, we're not going to call it a buffer. There are some more complicated examples that have polyprotic acids, and there's multiple conjugate acid-base pairs. But we're going to focus on the definition where it's only one conjugate acid-base pair for now. So we have a conjugate acid-base pair. Let me remember. So how would we... This is really weird wording on this slide. I think I did this in a small class, and I had something drawn up on the board. Oh, I remember. I actually had a whole bunch of acetate molecules. Let's do that. All right, we have a solution of acetic acid, vinegar. Is that a buffer? Yes or no? Is that a buffer? No, it has to be a mixture of both conjugate acid and base, and there has to be enough of both that it's at least 10% of one. If it's less than 10% of one of them, doesn't matter which one, it's not a buffer anymore. So, how do we take that solution of a weak acid and make a buffer? Talk to your neighbor. What are 2 ways that we can take that and make it into a buffer? We'll get into it. Don't forget. All right. Can I get 2 volunteers? What are 2 ways that we can take this solution? Let's say that there's water all around here and we have acetic acid floating around. How do we make that into a buffer? Well, what's one of them?
Add a dissolvable salt with acetate.
What do you guys think about that? So I'm going to add to this some of those guys. Does that make a buffer? What's going to happen to this salt when it's in water? It's going to dissolve. Remember, sodium is highly soluble. And we're going to end up with acetate. Is that the conjugate base of our weak acid? Yes. Do we have at least 10% of both of them? 90 to 10, down to 10 to 90, either way. Let's look at percentage. There's a total of 1, 2, 3, 4, 5, 6, 7 of them. 2 of the 7 are the conjugate base. That's greater than 10%. We're good. This is a buffer. Congratulations, I've made a buffer. All right? And that salt is something that you can go into the stock room and you can get a bottle and it's a solid crystalline thing and you can go dump it into water and you can make a solution. A lot of times, if you haven't worked in a lab, it's hard to understand or to realize this is not something that exists as a solid or liquid by itself. You cannot have a cation or anion. They don't exist. They exist either as a salt, so sodium on that, or they exist surrounded by water, and then they can be separate. But you can't just have acetate. It's not a thing. It's not stable. It needs a cation or something that's highly polar to surround it. So a lot of students would be like, oh, I just add acetate to this. You can't, right? But you do that by adding the salt of sodium acetate, which dissolves to give you acetate in water. Great, that's one way. What's the second way? So I'm going to go ahead and I'm going to erase that first way that we did this. Second way to make a buffer out of that acetic acid. Tripty?
Strong base.
Sentence?
Can we add NaOH?
How many would I want to add in this case? Okay, let's add 2 NaOHs. What happens when I add those? Strong base is sodium and hydroxide. So they fully disassociate. So we're going to kind of just do, sodium doesn't influence the pH. We have 2 hydroxides. What do those do now? Remember we said that any strong base will react with 1 proton, and that converts this one into, full-headed arrow, what's it going to make? and water. OH minus, H plus makes water. So that means that this guy is no longer there. That hydroxide is no longer there. That we only have the acetate. How many times is that going to happen? Which one's going to run out first? Right, that's what we ask ourselves. So let's go ahead and say the second one is going to attack this. It's going to generate a second acetate and some more water. We're not going to write out the water because it's surrounded by water. So what's the ratio of our conjugate acid to conjugate base now? 3 acids, 2 bases. Is it a buffer? Yes. 2 totally legit ways of making a buffer of acetic acid and acetate. And if we wanted to, we could say that because this came from sodium hydroxide, that it's actually a really similar way to make a buffer, because remember, sodium acetate had the sodium cations as well floating around. So both of these have spectator ions of sodium in the solution. Questions? So let's spend 1 second right here, and let's go back to what a pH does. Can someone remind us what a pH? What a buffer does? Corbin?
I don't want to answer.
Sarah? Okay. When? What happens? Jonathan?
When you add either more acid or base to it.
Great. So I'm going to clear this up. I'm going to simplify this just down to the buffer that we have, right? These 5 molecules. I'm going to clean up everything else. All right. And then I'm going to say, you guys want to add acid or base to this? Which one? Acid. We're going to add a strong acid, HClO4. 1 to the solution. Talk to your neighbor about what happens. Make a prediction of what happens. So I'm going to throw a little bit of a curveball in here and add one more question. If we put HClO4 into solution A, which is just pure water, what's going to happen to the pH? It's going to drop.
Just like that.
Because you added a strong acid to water, right? You're releasing a full proton. Every HClO4 dissolves into an H plus ion and a perchlorate ion. Second question that you guys were talking about. What happens in version B, where you put that into a mixture of a weak acid and its conjugate base? Anthony, what are your group's thoughts on this?
We haven't thought about it yet because you just asked the question.
That's the question I asked before. What happens when you put a strong acid into this mixture?
So, we know that it's going to fully dissociate strong acid into the H plus ion and the Foy ion. And then the H plus is going to react with the O negative of the acetate.
Okay, so going back to what we were saying earlier, anytime you have a strong acid in water, it becomes a limiting reagent problem. You now have 1H plus. It's seeking any base that exists. Do we have any bases? these are going to react. Do they both disappear? Are they gone? What do they make when they react? Right, and both of these are now gone. We used them up. Limiting reagent problem. So, in the top example there, we added a strong acid to water, and every molecule of strong acid releases one H plus ion. When we add it to this sample here, what happens to that strong acid, that one H plus? Christina?
I'm good.
What did you say?
No. I'm good.
I have a volunteer. What happens to that H plus when it goes into that mixture of a conjugate acid-base pair? Kayla? Echo?
It cancels out one of the moles of the base.
Cancels out might not be the word I'd use.
Will it turn?
So consume maybe. So keep going.
It consumes and then turns it back into one of the acid molecules.
All right, this is extremely crucial for understanding buffers. If you don't, this is really, really well said. A strong acid, in essence, converts one of your conjugate bases to the acid of that conjugate acid base pair. It doesn't use it up. It doesn't disappear, right? It's a conversion from this to this. So in essence, we add an H+, but instead we get out one of these. Which one is going to have a bigger influence on pH? The H+ or an acetic acid? It's going to have a much bigger influence on pH. So going back to some of the discussions, right? We minimize the change in pH. Instead of having a whole H+ released, we have a whole acetic acid released. For every acetic acid, what percentage of that is going to disassociate? What percentage of the time are we going to find that separate? Is it going to be 100% of the time dissociated into H+ and acetate? How could we find the percentage of dissociation of this one? Ka, and then we can do a nice table. But it's not going to be 100%. So what a buffer does is it takes a strong acid, by using a conjugate base, converts it back to the weak acid. We end up substituting basically a strong acid for a weak acid. How do you guys feel about that? So we're going to do some more discussions around this. If I had added a strong base instead, would the same thing have happened? Josh, do you have a question?
I don't want to ask in front of class, though.
All right, I'll come around. If we'd add a strong base instead, see how many of these I can go back. If I added one of these, talk to your neighbor about what's going to happen to the solution. All right, can I hear from someone who's a little hesitant but is willing to share on what happens in this super zoomed in version, which I got pointed out to me doesn't, like, it's a little unrealistic because we usually talk about moles and moles and moles of stuff, not individual molecules. So we're going to zoom back out and look at moles in a second. So for right now, we're just saying if we had this little microenvironment with these 5 molecules as a buffer, what happens if we add 1 molecule of calcium hydroxide to it? Can I hear from a new group? Christina?
I don't know if this is right, but like the CA I feel like is dissociated, and then you have 2 hydroxide ions, and then so I feel like the acetic acid would give.
Pause 1 second. Did everyone catch that? For every 1 calcium hydroxide that dissolves, we get 2 hydroxide ions. All right, don't miss the little stuff. Go ahead.
And then 2 acetic acids would have to both give off a hydronium ion to the hydroxides, because you have 2 of them.
I'm going to write the hydroxides out separate. So once again, a hydroxide is now scavenging for any acidic proton. One of the points that Josh brought up is that actually water, when this bumps into water, it is going to steal a proton off of water. But what does it generate when this steals a proton from water? Water and hydroxide. So this can propagate, it's called, through water by stealing a proton from this water, and now you have an OH minus here. And then it'll do the same with the next one and still have an OH minus here. So it doesn't end the reaction until the hydroxide bumps into something with an acidic proton. As soon as it finds that acidic proton, what's it going to do with that proton? It's going to consume it. Does that mean that acetic acid is gone?
No.
What does it become? It converts this to an acetate. And water. Our second one, do the same thing over here. Now that's gone. And we generate 1 more. Do we still have a buffer? Is it less than 10% of one of them? Nope. 4 to 1, we still have a buffer, we're good. If we had added 2 calcium hydroxides, would that still be the same answer?
We'd have a leftover OH.
We'd have a leftover OH minus, we would have no acetic acids left, and that would no longer be a buffer. We now have a solution of a strong base and a weak base. All right, so let's go ahead and do some calculations. Hopefully you're kind of following along with question 5. If we have a buffer, list at least 2 things that happen when you add a strong base. Let's actually go ahead and do that question. So go ahead and answer question 5. We're going to talk through specifically what I want to hear you guys saying on that. And then you guys can answer 4 kind of on your own, similar to what we did with acetic acid. So we're doing question 5A and 5B. Strong base.
If we said that it's about conjugate base
Or it can be a weak All right, can I hear from a new group? If we have a buffer, what are two things you can describe that happen when you add hydroxide to that buffer solution? Carol?
No, I have no clue.
Based on the conversation we just had, the buffer can either be a weak acid and its conjugate base, or a weak base and its conjugate acid. What are two things that can happen? Caleb? Share your thoughts and then we can go from there, because it's a starting point.
With the concentration of something.
Which one is going to decrease in concentration? So if you add hydroxide to solution, you're going to decrease the concentration of your weak acid. Or it could be, that can be a way to note your weak acid. If your conjugate acid base pair is a base and it's conjugate acid. Does everyone see what I'm getting at there?
No.
So I'm going to draw out two. So this could be one buffer, right, where we have a weak acid and its conjugate base, acetic acid, for instance, and acetate. Or it can be ammonia, it's your base, and this is ammonium. This is a buffer, or this is a buffer. So Kayla's point was, if you add hydroxide to this buffer, you're going to decrease the concentration of your weak acid. What if we had this bottom buffer instead? Which one would decrease in concentration? Do we decrease, if we add a strong base, do we decrease the concentration of our base? The conjugate acid. Okay? So it doesn't matter which conjugate set we have. If you have a conjugate acid-base pair, you have an acid and you have a base. They're both weak. So it's probably not clear the way it's written there. So let's say one thing we can say for sure that happens if you add hydroxide to a buffer is that you decrease the concentration of your acid, of your conjugate acid base pair. What else can you say happens? Christina, nice and loud.
The pH increases.
pH goes up. We add a base to water, it's going to go up. It's going to go up less than if we didn't have the buffer there in the first place. What else can we say happens? Jyoti?
Conjugate base.
What about it? Right, hydroxide will consume whichever is your acid, but in consuming it doesn't just go away, it converts it to the other one. So we can say the concentration of your acid goes down, your base goes up, and your pH also goes up. Say again? Where did I lose you guys? So if we have the top buffer, we add hydroxide, we use up HA, we generate A minus. So this goes down, this goes up, and your pH goes up because it's adding a base. Here we use up this, and every one of those generates one of these, so the pH goes up. Yes?
When you say decreases the conjugate acid, is it the same thing that we were doing before with the hydroxide cancels out the base when you were
It doesn't cancel it out. What does it do?
That's like cancels out, decreases the conjugate.
It converts it.
Converts it, okay.
From the acidic form to the basic form.
It was just confusing because we were drawing the diagrams and you were like Xing it out. I was like,
Yep.
what's the difference? acids.
But I X'd out and then I drew right next to it that there was a newly formed conjugate.
Got me on a technicality.
Fair. All right. Austin?
Just a quick question. Like, if you were to answer this on a test, and it was like one of different like response essentially, it's like if you put like the strong base would totally disassociate and be totally consumed, would that be inaccurate?
No, but that doesn't really necessarily speak to the fact of the mixture that is a conjugate acid-base pair. So I would like to have more than that. Does that make sense? Echo?
Does it matter, like, the example before with the calcium hydroxide, like, it had 2 moles, so it's, you know, like, to us, it was like, oh, strong base, because it had 2, you know, molecules to that molecule, or, you know, but, it doesn't really matter if it's a strong base or a strong acid, like, that you're adding into a solution with a buffer, like,
So your point, I think your point is about the stoichiometry, or is your point about being strong and what happens? Maybe let's do the second part of this question, and then maybe this will relate back, because you were talking about a strong acid or a strong base. So if we're saying the same thing, if we have a buffer and we're adding strong acid that generates H plus ions in solution, what are some things we can say that happen that change in that solution? I'm going to give you guys 30 seconds, and I'm calling on Laura, Chelsea, and Savannah.
I'm not, I'm still recording with that, so therefore your excuse is not.
You're getting it right, but like, let's make a weaker conversion. No, it's just weird. Like to say, oh my gosh, okay, what's so stupid? No, I didn't.
All right. I want to hear 3 changes that happen to a buffer when you add a strong acid. Start, Savannah.
Decrease the pH.
pH decreases. We're adding an acid to any water. It's going to decrease the pH. Lauren, what else happens?
The strong acid is going to react with the base to create.
Wait, stop. Okay, so strong acid reacts with the base of the conjugate acid-base pair. And then last one. Norina, would you like to? Or Danielle, Bree?
I think that it's going to decrease the concentration of the base and increase the concentration of acid.
Great. So those are kind of the 2 separate things, right?
Converting the conjugate base to like acid.
Perfect. I love the way you said that. The strong acid converts the conjugate base to the conjugate acid. And I keep calling both of them conjugates because I really don't want to get stuck in, is it a weak acid in its conjugate base or a weak base in its conjugate acid?
I was wondering, I think that's what she was trying to ask, but I was wondering that same thing. So if you added instead of a strong base to the buffer, but a weak base, what exactly is going on there?
There's a lot of equilibrium that happens there, and it's not nearly as straightforward.
So we don't have to worry about
So that is not a titration, that's not how you make a buffer, that is not a single solution buffer, that is a complex buffer. And those are made, and there's benefits to having those, but in this class we're not going to be talking about making those.
That's okay.
So we look, like we're saying, we're adding a strong acid to these buffer solutions or a strong base, just to like guarantee they can associate and consume the
Correct.
other.
So if we don't have a strong acid or a strong base we're adding, then we can't say it 100% reacts. So then it becomes an equilibrium problem, and then it becomes much more complicated. Fair question. All right, think you guys can apply this now to mathematical operations?
This is where you lose me especially. It's so nice to go 1 for 1.
Let's go ahead and answer a high-level conceptual question before we move on? A couple more seconds. Closing up. All right. Lynn, can I get you to share your thought process on this?
Because of buffer's definition is that it makes the change in pH smaller. I should be.
Okay, great. I concur. Do you want to go one step beyond and explain why? What's happening molecularly with that?
If you're adding a strong acid to a beaker with a buffer, the strong acid is going to disassociate fully and react with the conjugate base, and an increase in the concentration of a weak base is going to change the pH less than the addition of a strong base or a strong acid.
Okay, I think you flipped it at the very end there.
Yeah, sorry.
No, I think, so what you were saying was that when you add a strong acid, it reacts with the weak base to make some of the weak acid. So you're basically substituting a strong acid for a weak acid, and a weak acid is going to have a smaller effect on pH. Fantastic. Very well said. All right, I want you guys to be able to visualize that. And I have a visual that hopefully will help. If we have a buffer, right, we have a mixture of these two guys. We have some hydronium. This is actually going to be a really, really, really small amount. That looks like way too much. So if we add hydroxide, what's it going to do? The way we've been talking about it, what's it going to react with? So there's two different ways you can look at this. Humphrey? Is it going to react with H3O plus or HA? Whichever it sees first. If it uses up this, what happens to these concentrations? If products get used up? Le Chatelier's principle, right? Shifts everything to the right. Or the other way, what Jonathan was talking about, the way we've been talking about it is that you're going to consume some of the HA. That part of the HA that gets consumed is converted from OH minus to A minus. Which basically shifts. So the way, there's multiple ways to think about this, but the way I do is that we use up some of this, we move it over here, we start with OH minus, now we have more A minus. Or if we add H3O plus, what's that going to react with from a strong acid? I love these animations. And notice that the size of the box, the concentration, number of moles of our strong acid are exactly the same as the number of moles of the new weak acid that we generated. So hopefully you're noticing also that this box is changing size, so the pH will shift slightly as well. This is way oversimplified. I would get berated by some of my colleagues, but I'm hoping that you're seeing, consuming one thing, moving it to the other side. We're converting from one thing to the other. So let's go ahead and work on question number 6. Before we do too much math, let's estimate. You might need to do a little bit of math. You're welcome to do some. But then before you do a whole bunch of calculations, I want you to figure out what you expect here. And maybe why I'm asking this specific question. If you get stuck, please raise your hand. This is one of those amazing questions where you're just so happy to be a teacher. I feel like you've done a really good job. All right, take another 20 or 30 seconds and really think about how you could solve this problem and get a ballpark idea. And then we're going to talk through it. But please get something down on paper to at least think about how you'd approach it. All right, let's go ahead and talk through this one. First question. Is this a buffer?
Yes.
How do we know it's a buffer, Moab?
Because there is a less than 10% difference between the weak acid and the conjugate base. I mean, more than...
So even before you go into the numbers, right, that's maybe a second step. You say, notice that there's a weak acid because there's a carboxylic acid, CO2H.
Yeah.
And there's a CO2 missing the H with the sodium there. So we have a conjugate acid-base pair. And then you say, well, is there enough of both to make it a buffer? How do we... And lose the Na because it's in water. So how do we figure out if there's enough of both of them? We have different molarities. Is that what we look at? Ruby, what do we do? We need to know how many moles of each one. And in the end, we need to know the molarity of each one. Remember, molarity is the moles per liter of solution. What's the final volume of our solution? 300, right? 250 plus 50? 300.0. Just saying. Right? We don't throw away that in safe edition. All right, so we have 300 milliliters. How many moles of each do we have? Did you guys calculate that? So if you guys go back all the way, you say you have 50.0 milliliters. And then our concentration, we're going to unpack that every time we use it. 2.00 moles. Is that right?
Would it be 6.40?
Say again?
Not in this
On the next one. Liters.
Okay, yeah, the next one is 2 sig figs for molarity. All right, and how many moles of the other one do we have? And then what's the volume of each of those? We can. Or you can do and then we cancel out, or we make sure to keep the milli in mind. So at this point in Gen Chem, I'm not going to do conversion from milli to liter, but you need to make sure that you do that appropriately in order to get the right units when you come out. To Sarah's point. So if I put this in my calculator, I'm going to do 0.100 over 0.300 because I know the final unit needs to be liters. If you need to do the calculations separate and do the conversions, you're welcome to do that, but I'm not going to be showing those steps individually. All right? You guys have done it enough that I think you're comfortable with it. So each one of these is, what, 3.33? No. 0.333 molar. That's not an M. So, what is the pH? Why did I put these three different options for your pH here? Why did I not put greater than 7, less than 7, equal to 7? Lindsay? Any idea why I didn't put pH equals 7, greater than 7, less than 7 like we do a lot of times? So, what Moab said first, we identified it as a buffer. Because we identify as a buffer, we're going to use that equation to find the pH. And if that ratio is 1 to 1, our pH is going to be equal to pKa. The ratio is off, we're going to have pH greater than pKa or less than pKa. Alright, so what's our pH for this? You guys go ahead and click that in. So go ahead and click in what the pH of the solution actually is. You have until 1 minute 30 seconds on there to click in the pH. Couple more seconds. Closing out. All right, we had a lot of different answers, but I saw two of the main ones that were floating through were 4.75, 4.74. Where do we get those? Negative log of the Ka. So when the concentrations of the conjugate acid base pair are equal, our buffer is going to have the pH of the pKa. That's weird. So that's not what I wanted to do. All right, next question. Top of the back page. To that solution, we're going to add 1 milliliter of 1.00 molar, or 1.50 molar calcium hydroxide. Calculate the pH after addition. And I'm going to do one step in between first. We're going to take 1 minute, and I want you to use these prompts up here to click in after question number 7 happens, what is the pH of that solution going to be out of these 3 options? And think about why I'm asking about these 3 options. And then once you've clicked in your answer, then go and actually calculate what that value is. All right, a couple more seconds to answer from these options after we add the, what's in question number 7? What's going to happen? Closing out. All right, let's regroup real quick, and then I'm going to have you guys work on the second part of the problem. So can I hear from a group, new voice, please? What is going to happen to pH after we add stuff to this original solution? Which of these options is going to be appropriate? Danielle. So which of these options would be fitting to that? Great. Why? Why does the pH increase?
Well, on the other page, you said if you add a strong base, the pH will increase, and we're adding a strong base. So.
Yeah, and just logic, right? We're adding a base to water. Doesn't matter what's in the water, the pH is always going to go up. It's in a buffer, so it's going to go up a little bit. So think about numerically your answer is going to have to be greater than pKa, but maybe not by a huge amount, we don't know. So then how do we figure that out? This is where we're going to start using our ICF tables. What kind of a problem do we have right now? It's an acid-base neutralization. One is a strong. All right, what is going to react with what? So the first thing that we should do is remember that calcium dissociates into hydroxide. Calcium hydroxide associates with calcium hydroxide. What am I missing? All right. So how do I know? I know how many moles of our conjugate acid and conjugate base, right? We have 0.300 moles of each of those. How many moles of this do I have? How do I find that? I didn't quite hear you.
Do what you basically did for the second one where you multiply 1.5 by 1, and you would divide by 301 instead of 300.
We're not getting at the 300 yet. So here's the thing we have to remember. When we do limiting reagent stoichiometry, the volume is irrelevant. Once we know how many moles of each we have, we need the volume to find the number of moles. Once we have the number of moles, if you have 7 of one and 2 of the other, you're going to use up 2 of each, right? So we need to know the number of moles. So if I use my 1 milliliter to find the number of moles of calcium hydroxide, can I just compare that number of moles of calcium hydroxide to our moles of conjugate acid base pair? How do I use that top equation in this one here? Do we care about the number of moles of calcium hydroxide? What do we really care about? Hydroxide. So what's the next step? Remember stoichiometry for a semester? Hopefully. So how many moles do we have? What does this come out to? So 3 millimoles. You guys okay with that? Or 0.00300. So then our second to last step, what do these do? Are they going to react with the acid or the base of the conjugate acid-base pair of the buffer? So I'm going to say that we have hydroxide reacting with, what kind of arrow do I draw? And then I make water, which I don't really care about because it's in water, and so here's where I'm going to show you a tool for limiting reagents. How many moles do I have initially? What's the change in number of moles? And what's the final number of moles? I know this looks like a nice table, it's not. So I'm going to use millimoles. I know you guys hate milli, but we have 3.00 millimoles of hydroxide. We have 300 millimoles of acetic acid. Do you guys remember that? And we're going to say for now that we have 300. We know how much we have on each side, right? What's our limiting reagent? Which one's going to run out first, hydroxide or acetic acid? So the change is minus on that side. How much? So 1-to-1 stoichiometric ratio. And then how many moles do we have in the end? Remember, this is all about moles. Any hydroxide? 303. We don't care. Oh, sorry. 297, 303. Is pH still going to equal pKa? How do we find out? Do you know the final volume? Wait, was it 3? Shoot, did I mess this up? How many moles did we have to start with? Was it 1.1 moles, not 0.3? You guys catch what I did wrong?
No, not yet. We did volumes.
So this should be a 1. It was 100 millimoles of each, which would mean you'd have 97 and 103 in 300 millimoles. Can you find the pH of the solution? What's on the top? What's on the bottom? So now, instead of pH equals pKa plus log of 1, we have plus log of this ratio. Remember, on the top and the bottom, you have the same volume. So in essence, you can kind of just say the ratio of the moles to find your pH. All right, so for your homework for Wednesday, you have some practice with this. I just really wanted to get through this one problem. If you do this calculation, pH is going to be slightly higher than pKa, so it works out. So try to wrap your head around what we did today. Try to practice on it for Wednesday. Post questions and discussions if you need to. Thanks.